and stages of thunderstorms, as well as the many associated hazards to aviation. In addition, we will discuss avoidance procedures and precautions for flight in and near thunderstorms. All thunderstorms develop through three distinct stages: the cumulus stage, mature stage, and dissipating stage. In the beginning cumulus stage, rising moist air causes clouds to increase in vertical height, with strong updrafts preventing moisture from falling. Within approximately 15 minutes, the developing thunderstorm reaches its second mature stage. At the mature stage, drops of moisture such as rain or ice are too heavy for the cloud to support and begin to fall, forming rain or hail. As the precipitation falls, it creates a downward motion of cool air. A mature thunderstorm includes warm rising air and cool descending air, as well as severe turbulence within and near the cloud. This is the most violent period of a storm's life cycle. As the vertical motion near the top of the cloud slows, the cloud top spreads and takes on an anvil-like appearance. At this point, the storm reaches its third and final stage. During the dissipating stage, downdrafts continue and spread out, replacing the updrafts needed to sustain the thunderstorm. Pilots may encounter thunderstorms of varying size, severity, and type. The four types of thunderstorms are classified as single cell, multi-cell or thunderstorm cluster, squall line, and supercell. A single-cell storm often develops on warm and humid summer days and is comprised of one discrete thunderstorm cell. Although often referred to as a common thunderstorm, these individual cells can still be severe enough to produce hail and microburst winds. A thunderstorm cluster or multi-cell storm develops in extended clusters with numerous cells that can cover a large area. With this type of thunderstorm, it is possible for individual cells within the cluster to move in one direction while the whole system moves in another. A squall line is comprised of a narrow band of active thunderstorms. It most often develops on or ahead of a cold front in moist, unstable air. However, it may develop in unstable air far removed from any front. Squall lines may be too long to easily navigate around and are often too wide and severe to penetrate safely. Least common, and potentially the most severe, supercell thunderstorms are a single, long-lived thunderstorm characterized by the presence of a deep, persistently rotating updraft. Supercells can last for hours, achieving a quasi-steady state that can produce dangerously large hail, torrential rain, and substantial downbursts. In addition, the deep rotating updraft within a supercell frequently produces tornadoes. In addition to the expected low ceilings and degraded visibility, thunderstorms can include just about every weather hazard known to aviation. These hazards frequently occur in numerous different combinations. It is often impossible to visually determine which hazards exist within a given thunderstorm. Therefore, extreme caution must be exercised whenever flying in the vicinity of any storm, regardless of type or apparent severity. Tornadoes can occur in association with both isolated thunderstorms, such as a supercell, and squall-line thunderstorms. As tornadoes form, strong winds gather dust and debris, and the low pressure within generates a funnel-shaped cloud that extends downward from the cumulonimbus base. An aircraft entering a tornado would almost certainly suffer loss of control and structural damage, as vortex wind speeds are estimated to exceed 200 knots. Since the vortex also extends up into the cloud, a pilot flying inside a storm could inadvertently encounter a hidden vortex. Turbulence is present in and near all thunderstorms, with the strongest turbulence found within the cloud. Outside of the cloud, shear turbulence can be encountered several thousand feet above and up to 20 miles laterally from a severe storm. In addition, clear air turbulence can be encountered 20 or more miles from the anvil of the storm, and areas of low-level turbulence are associated with gust fronts up to 15 miles ahead of the storm's precipitation. Wind shear and damaging microbursts can also be found in and around thunderstorms. Powerful updrafts in thunderstorms support great quantities of water in the form of large droplets. When these droplets are carried above the freezing level, they may supercool and freeze immediately on impact with an aircraft. The rapid formation of clear icing can occur at any altitude above the freezing level, and encounters can be frequent in a cluster of thunderstorm cells. Hailstones of significant size can also develop from these droplets and can be encountered even when in clear air several miles from the storm. Significant damage to an aircraft can occur within just a few seconds when encountering hailstones larger than 1/2 inch or 1.27 centimeters in diameter. Though serious accidents due to lightning are extremely rare, lightning strikes are known to occur and can be very hazardous. A lightning strike is capable of puncturing the skin of an aircraft and can cause damage to communications and electronic navigational equipment. In some rare cases, lightning strikes have even been suspected of igniting fuel vapors and causing an explosion. Even if not struck directly, nearby lightning can momentarily blind the pilot and render them temporarily unable to navigate. Nearby lightning discharges can also disrupt radio communications of low and medium frequencies. An aircraft's turbine engines have a limit on the amount of water they can safely ingest. Severe storms can contain areas where the water concentration in the air is so high that it exceeds the water quantity ingestion limits of the aircraft's turbine engines. This could result in one or more engines flaming out or failing structurally. As a thunderstorm approaches, pressure falls rapidly, then rises sharply with the onset of the first gusts and heavy rain. This cycle of pressure change can be so rapid as to occur in just a matter of minutes, resulting in altimeter readings that may be more than 100 feet in error. When trying to avoid thunderstorms, remember to use weather reports and forecasts to supplement airborne radar. Scattered thunderstorms that are not embedded can be seen and circumnavigated. Thunderstorms can be visually identified by the shape of the cloud and frequent occurrence of lightning. Once you have identified a thunderstorm, you should try to adhere to the following guidelines. Do not try to fly over or under a storm. Flying under a thunderstorm, even if you can see through to the other side, could result in extreme turbulence or a wind shear encounter. Trying to fly over a thunderstorm may exceed the altitude capability of your aircraft. Again, the best way to avoid a thunderstorm is to circumnavigate it. Keep a distance of at least 20 miles upwind from a severe thunderstorm, especially the anvil of a large cumulonimbus. Without the use of airborne radar, do not fly into a cloud mass containing embedded thunderstorms. Also, regard any thunderstorm with tops exceeding 35,000 feet as extremely hazardous. Above all, never regard any thunderstorm as light, even when radar returns indicate light intensity. If a thunderstorm cannot be avoided, there are several actions that should be taken prior to entry into the storm. First, tighten your safety belt, put on your shoulder harness, and secure all loose objects. If able, establish an altitude below the freezing level or above the level of minus 15 degrees Celsius to avoid the most critical icing conditions. Verify that anti-ice systems are on and operational. Establish power settings for turbulence penetration airspeed recommended in the aircraft manual. If using automatic pilot without a turbulence mode, disengage altitude hold mode and speed hold mode. Automatic altitude and speed hold modes tend to make the aircraft chase both altitude and airspeed, thus increasing structural loads. If using airborne radar, tilt the antenna up and down occasionally to detect thunderstorm activity at other altitudes. Once a thunderstorm is entered, remember to monitor the flight instruments. Maintain a constant power setting for the recommended turbulence penetration airspeed. Let the aircraft ride the waves. Do not attempt to maintain constant altitude. Most importantly, do not attempt to turn around once you are in the thunderstorm. In most cases, the fastest way to transition through a storm is to fly a straight path. A straight path also reduces stress on the aircraft, as turning maneuvers in a thunderstorm can result in structural damage.